Welcome back. In this video, we're going to discuss the most complicated loading situation that we're going to deal with in fatigue, and that is when our cycles do not match up. So previously, when we've been talking about cyclic loading, and even when we had combined loading of different types, we needed them to all be within the same time frame. So if we are considering the bending of a shaft, usually the cycles is the rotation of that shaft as it spins around, and it might be carrying a torque. Now that torque can go on and off, but it's basically constant while that shaft is spinning. So now we're going to look at what happens when we have more complicated loading, more complicated patterns in our cycles. So for example, consider a part that the loading scenario looks like this. For a certain time, the stress fluctuates. We'll call this 40 and 80, and we'll call this negative 20 and negative 60. So for a certain amount of time, we see some fluctuations. And then at a different time, because of the way the shaft might be mounted, all of a sudden it sees a different force. And it may fluctuate with different types of cycles. And so on like that. What we can see here is that we actually have several different types of cycles. So the most obvious ones that we can see are between 40 and 80. There's clearly a cycle there. So there's one cycle which goes from a sigma max and a sigma min. We'll build a little table here. There's clearly one cycle that goes between 80 and 40. There's clearly a cycle that goes between negative 20 and negative 60. But hopefully you see that there's also a cycle between the maximum and the minimum. So that might not be intuitively obvious, but as we go from, anytime we go from a maximum to a minimum, we have a cycle. So there's a sort of hidden cycle in there as well that goes from 80 all the way down to negative 60. And in fact, this is actually going to be the most damaging cycle. So the hardest part about doing cumulative damage or multiple cycles is figuring out where the cycles are. So there's lots of different methods for doing that. If you're just looking at data, usually you can take frequencies, and you'll find, first of all, the primary frequency, that's the largest one, the biggest difference between values. Once you take that out of the picture, then you can look at the next one, and so on like that. So if you're doing this in the field and you're taking experimental data, you'll often see lots of vibrations. And the smaller the cycle is, the less likely it's going to be damaging the part. So what's most important is to catch the biggest cycle. So again, just to fill out this table, we could see that we have some mean and some averages here, which may cause different values. So the mean and average between 80 and 60. So the mean between 80 and 60, or 80 and negative 60, is 10, and the amplitude is 70. The mean between 40 and 80 is 60, and the amplitude above that is 20. And the mean between negative 20 and negative 60 is negative 40, and again, an amplitude of 20. So we can look at any one of these cycles and figure out, based on our things that we already know, whether that's going to cause damage or whether it's going to lead to finite or infinite life. So what we've done previously is just sort of assumed that we can ignore these parts because they're so much smaller compared to this one. So what we're going to present in this video is called the Miner's method, or it's the cumulative damage method, and it's the way to deal with these things and not ignore them. So what we're going to do is assume that every cycle this part goes under is going to cause some amount of damage, and then we're going to add all of that damage up and see if it equals the point at which a part would fail. So we need to establish a framework of the number of cycles under each type of loading it's going to experience, and compare that to the number of cycles it would take at that loading to cause failure. So let's look at an example to make this a little bit more clear. All right, let's consider a steel bracket that we're in the process of designing. So we don't know much about it, but I'll give you some simple loading to begin with. So let's assume it has fully reversed loading at a couple different cycles. And the reason I'm starting with fully reversed is it's a little bit more simple to deal with. So it has a fully reversed cycle where sigma 1 max is 420 megapascals, sigma 2 max is 350 megapascals, and sigma 3 max equals 280 megapascals. And all of these are fully reversed, so the mean's going to be 0, and the amplitude is the same thing as the max in this case, again, just for simplicity. So the number of cycles we want this thing to last at each of these is we expect this to go 5,000 cycles at this loading. At the second loading, we want it to go 20,000 cycles. And at the third type of loading, we want it to go 30,000 cycles. And these are all cycles. So our objective here is to figure out what to make this thing out of in order that it will not fail. So this is a design problem, and we're going to have to make some guesses along the way, since we're approaching this problem with very little evidence. So our solution approach is going to be to look at the number of cycles we believe it would last at that level of loading. So that's the fully reversed stress over A raised to the 1 over B, where A and B are evaluated the same way we've done before. A equals the F ratio times the ultimate strength squared divided by the endurance strength, and B equals negative 1/3 times the log of the F ratio times the ultimate strength divided by the endurance strength. So the damage we're going to calculate from a combined amount of loading is the sum of all the pieces of loading. So we'll do sum, and this is the number of cycles for a particular stress that we're at compared to the number of cycles that it would take for that part to break. So basically what we end up doing is we say from cycle 1 we get a little bit of damage D1 plus cycle 2 we get damage 2 plus so on and so forth. And when this factor D, when this value D equals 1, we consider the part to fail. Now note this is obviously a linear assumption that we can add damage on top of damage, and it just kind of piles on, as opposed to more of an exponential model where as you add a little bit more damage the part becomes significantly worse. So this is a linear model. There are other models of predicting damage that are out there, but this is by far the simplest and historically the most common. So let's go ahead and apply it to our problem and see where that gets us. We need to sort of start with the material, and if we don't know what to make it out of, we can build an Excel table and pick a value, or do the same process to multiple material types in a table. But let's do an example here, and say we picked randomly 1050 cold drawn steel, which has a yield strength of 580 megapascals and an ultimate strength of 690 megapascals. In order to find out the number of cycles this thing will last, we're going to need to know SE, and we're going to need to know that F ratio. and then we can figure out the number of cycles that will last each one of those. So for our endurance strength, we know it is approximately half of the ultimate strength for the hypothetical. And then we have our Marin factors, Ka, Kb, and Kc. So as a first pass design, we don't know what to make this thing out of. We don't know what machining process we're using. We don't know exactly the sizing that we're dealing with. We only know sort of the stresses that are being applied here. So as a first pass, let's approximate the Marin factors to something reasonable that they are in. So this is an approximation. We'll call all the Marin factors 0.8. We can come back when we know more about the system and change these. As we'll see, the reduction of the endurance strength is pretty typical for most values. All right, so if we did that, plug in our 690 megapascals and do 0.8 for each one of the Marin factors, we'll come up with a guess of our endurance strength around 176 megapascals. All right, so this is our guess, and we'll want to come back and fix this if we choose new materials or we know more about our system. All right, so how much is one load going to last? Well, we said that n, the number of cycles, is equivalent to the Fourier reverse stress, or the equivalent Fourier reverse stress. In this case, our equivalent is the same thing as what it is, over a raised to the 1 over b, where our a and b values are performed. So in order to calculate how much each cycle will, how many cycles we can go at each type of loading, we'll need to calculate our a and b values. So a equaled F times the ultimate strength over SE. So let's find or guess a pretty approximate F. So based on our ultimate strength of 690 megapascals is our SUT. From the tables, F is about 0.84. So putting those together, we have 0.84 multiplied times the ultimate strength of 690 megapascals, and divide that by the endurance strength we just calculated of 176 megapascals. This is squared up here. That should give you an A of about 1,902 megapascals. And do the same thing for B. Negative 1/3 the log, and F is 0.84 times 690 over 176, which equals negative 0.172. All right, so these values won't change as we look at different cycles, since it's the same part with the same endurance strength and the same ultimate strength, but we'll calculate the values separately each time. So for N1, that is the number of cycles that will last at that first level of loading. We need to calculate the loading at that level, which is 420 megapascals, divided by our A, which is 1,902 megapascals, raised to the 1 over negative 0.172. This gets you about 6,479 cycles. It's a little too precise, but we'll call that 6,480 cycles. Again, we probably don't need to be this precise with it, but we'll see how this adds up in the end. All right, you can do the same thing for the second cycle that we identified. So that stress value was 350 divided by 1902 and raised to the 1 over negative 0.172. That'll be approximately 18,000 cycles, 700. And finally do the same thing for N3, which was 280 cycles, 280 megapascals over 1,902 raised to the 1 over negative 0.172. Approximately 68,000 cycles. All right. So none of these are going to, at any of these loadings, would we expect to see infinite life out of this product. But what we do see is that the stress is going to lead to failure eventually. So let's calculate the total damage from each of the cycles. So the total damage is, again, the sum of the number of cycles it's at that state compared the number of cycles it should last till failure at that state. So recall that we said we wanted this part to last at the first level of loading, 5,000 cycles. At the second level of loading, we wanted it to last 20,000 cycles. And at the third level of loading, we wanted it to last 30,000 cycles. Now we can compare that to the amount of cycles it takes for this thing to break, which is what we just calculated. So 6.5 times 10 to the third cycles compared to 18.7 times 10 to the third cycles, and compare 30 to 68 times 10 to the third cycles. We're going to add all those things together as fractions. So if you think of this in terms of its life, so this one uses not quite all of its life. 5 over 6.5 is about 80% of its life at that cycle. 20 over 18.7 is going to be larger than 1, so this is going to cause, this is well over the amount of loading that will cause it to break. And 30 over 68 is a little bit more than half, so this is about the half of its life. So already we're more than the product's life will last. But if you add those pieces together, the damage equals 2.28, which is greater than 1, meaning that we are talking about finite life, or it will not last. This material, if we choose to make it out of this, will not last the desired number of cycles. So if this is a design issue, what we want to go back through is identify ways to either reduce the stress values, reduce the number of life cycles we expect it to experience, or improve the material properties. Those are all design variables that we are allowed to change. So another question we might ask is, how finite are we talking about? Or how finite is the life? So if we have 5 cycles, or 5,000 cycles, 20,000 cycles, and 30,000 cycles, those were the cycles that we wanted to get out of that. We kind of need to understand when these cycles happen. So of all of the cycles that this thing experiences, 5 represents about 9% of the cycles, 20 represents about 36% of the cycles, and 30 is the other 54.5 cycles. Obviously, there's some rounding here. So when will this part break? So if we are sequentially loading it, that is, if we consider the part, it will go through 5 cycles at that high level, and then it will start doing 20 cycles. As soon as D equals 1 from the addition of those two, then it will break. So we won't ever get past through all 20 cycles if we did it sequentially. If instead we were doing it at the same time, that is, if the loading cycle looked like the example that I began with, then we can compare the number of cycles that it will actually take to get us there. So we know the cycles that damage will be happening at about 9% of the cycles that it's going to go under. So if this is the same time, then N1 equals N2 equals N3, right? So all the cycles that it's going to be happening at the exact same time. So we can solve for what N is and look at that damage. So we know we're going to spend about 9% of our time in cycle 5 if these are happening at the same time. And we know we're going to spend about 36% of our time at cycle 2, and then finally 54% of our time at cycle level 3. So if we assume that damage will occur when this equals 1, we reach the end of the product's life, we can turn this around and solve for N, where we have N equals 0.9, 0.09, it's 9%, over our 6.4 thousand cycles plus 36% of 18,000 cycles and 54% of lasting 68,000 cycles. If we do that and solve for N, we find out that if all of these cycles are happening at the same time, the product should only last about 4.6 times 10 to the third cycles. All right, so let's recap a little bit on what we've done. When we have a part under multiple types of cycles of loading, whether those happen sequentially or at the same time, if we want to consider all of them, we have to do what's called the minor's rule. And minor's rule is this thing right here that says the damage can be added onto each other. So we take the damage that happens at cycle 1, the damage that happens at cycle 2, and so on for all of the cycles. And the hardest part, I said, is to identify what those cycles are. So once we find those, we can figure out the number of cycles we're taking at a particular cycle level and compare that to the number of total cycles it would take for that part to fail. And then look at that for every single type of cyclic loading and add them together to evaluate how much damage is occurring from each type of loading. So in this design problem, we will, again, need to either choose a stronger material, reduce the stress by perhaps changing the shape, or we can reduce the expected life or that we expect to get from the product. Well, that'll about do it for this video. Until next time.